Here we're going to look at a couple more differentiation rules, which will expand the number of functions we can find the derivative of. This first one is the sum difference rule, which is simply saying if I want to take the derivative of a sum or difference of functions, I can actually just go take the derivative of them separately and then add or subtract depending on what I was doing to begin with. This is not hard to derive simply because your function is f, let's just say plus g. The definition is you take the limit as t approaches x. So this whole thing is my function. And so it's my function of t minus my function. I'm using big F to represent that sum or difference, t minus x. So what I get is the limit as t approaches x, f of t, big F, is little f and little g evaluated and then added together, minus f of x is little f and little g of x added together. And then what I can do is take the limit as t goes to x. I can take the f and the f, t, and f of x together, f of t minus f of x. And I can take the g of t minus g of x. I didn't leave myself enough room here. And see, that's all over t minus x, but as long as I keep a common denominator, I can split that up. And so I'm taking the limit of something like that. Well, we know that the limit will pass to both of these terms as long as both these exist, and it's saying the functions are differentiable. So what I'm going to have is the limit of this, which looks like f prime of x, and the limit of this, which looks like g prime. So that's just a quick sketch of how you would show that this is true for plus or minus. And a very similar thing happens here. It's all coming from the fact that limits of sums and differences, you can take the limit separately, and the same with a constant. When you're taking the limit, the constant comes out. So this is saying essentially take the constant out of your way, don't worry about it until you're done. So that gives me, if I have my function is just a basic linear function, mx plus b, that's a line with slope m. This is saying that I can take the derivative of that by taking the derivative of mx by itself plus the derivative of b. That's using the sum rule because there's two terms there and I can take derivative of each term separately, where m's the slope, and so that's a constant, so I can say that that's the slope times x. So this is just putting in all the steps, and so what I get then is derivative of x we saw in the last one. This is one, you can use the rule and just remember derivative of x is 1. So this is going to be m times 1. Derivative of b, which is a constant, that's 0. So I get m. So we used that in an earlier video that the slope of the slope of a tangent line is the slope of a line. So if you have a line, you don't really have tangent lines. The tangent line, the derivative will be m for all points on that line. Well, here's a couple of other examples. What this allows me to do is take all my power functions together and any constant in front of it. So any polynomial I can now take the derivative of. If I want to find the derivative of y with respect to t in this function, I got to use the rule that I can take each one separately. Now you don't have to show this for every one, but I'm going to do it for this first one. Minus the derivative of this one plus the derivative of this one. But each of these, ignoring the constant, that is imagining the constant coming out in front, all I have to do is take the derivative of t squared. So I'm going to have 3 times 2t from that first one using the power rule. Take the 2 out in front, reduce it by 1. That's what I did here. This next one's a linear term, so all I get is the constant. And then the last one is a constant, so I get a derivative of 0. So this ends up being 6t minus 2. So that's my derivative for that function. This one again, be careful not to just go in and take the derivative of x and derivative of top separately. Remember, we don't have a quotient rule that works that way. We don't just get to take the derivative of top and bottom. Even though that works for limits, that doesn't transfer to what we're doing with derivatives. So I've got to, if I want to do it at this point, I'm going to have to break this up and rewrite it as the derivative of 5x over x plus 2x squared over x. So I'm separating that fraction so that I've got two fractions with a common denominator. You can do that with any fraction. You can always break it up over its denominator. Then reduce each one, because now this first one is just going to be 5. The second one is going to be 2x. And so now I can take the derivative. Derivative 5 is 0. Derivative 2x is 2. So the derivative is 2. If that had been like x squared down here, then notice, let me just do that one. Suppose I have x plus x squared. Let's go with divide that by x cubed. Let's divide it by x squared. So what I was going to show is that this one, when you split it up, you get x over x squared plus x squared over x squared. And what you get there is the derivative of 1 over x plus 1. And I'm doing this so that you can say, oh, it's a good thing I memorized what the derivative of 1 over x is, so I don't have to go through all the work. Derivative of 1 over x is minus 1 over x squared. Derivative of 1 is 0, so this is minus 1 over x squared. So you can see I can get two different functions having the same derivative. We'll look at that later. Notice we know that that's the derivative of 1 over x, but it also was the derivative of this function that I started with here. They're not the same function. I'll give you that hint. All right, well, the next thing I want to look at, this says, given this function, I want to find all the horizontal tangent lines. Find the x's where this thing has horizontal tangent lines. And we remember, you'll have horizontal tangent lines when things like this are happening. It turns out you can have one like there too. But so what if I want to find the horizontal tangent lines? What I need to do then to solve this is I need to figure out when the derivative is 0. Well, the derivative of this function, let's do that, f prime of x for this function is this power rule. Take the 3 out in front, reduce the exponent by 1. This is minus, well, that's 3x, so you're just going to get 3. Derivative of x is 1. And so what I need to do is solve this equation then, that 3x squared minus 3 equals 0. Well, here I can factor out a 3. This will then factor as a difference of squares. And the only way this will be 0 is for x to equal 1, or x equal minus 1. 3 can't ever equal 0. So when I look at this graph, whatever it looks like, at x equal 1 and minus 1, it has some sort of horizontal tangent line. So something like this is going on that graph, one of these 3 places, something like that. All right, the last thing here we're going to look at is the derivative is a function, and we can take derivatives of functions. So I can take the derivative of the derivative, and when we do that, we call that the second derivative, and that's what I'm showing here. The second derivative is the derivative of f prime, the derivative of the derivative. And we denote it as f double prime. Well, there's no reason I have to stop. If every derivative gives me a function, then I can keep taking derivatives. So you can take higher and higher derivatives. You can take third derivatives and fourth derivatives and 100th derivatives. And there are places actually in mathematics where we have to do that. So those are called the higher derivatives. And the notation is you use the double prime. This ddx notation is kind of weird the way it comes out. You get d squared f dx squared, which those aren't really squares. Those are just denoting second derivative. Or if it was third derivative, I'd put a 3 there. Same way here. This is second derivative of y with respect to x. We put the 2's there just again for notation. I don't like the x squared in the bottom because it looks like you're trying to say something about x squared. It would probably just be enough to put the 2, but that's not how it's done. And nobody asked me. So here's a function. I want to find the second, third, and fourth derivative. Notice with the fourth derivative, it gets a little bit cumbersome if you keep trying to put primes and somebody has to count all those primes. So usually after 3, they denote the derivatives as parentheses. It looks like an exponent, but that's why the parentheses are there. So hopefully you don't confuse it as an exponent. So anyway, I have to have y prime if I want to find y double prime. Well, again, we just use our nice power rule. Take the 5 out in front, reduce the exponent by 1. That's the derivative of that first term. Next one. Got a constant we can ignore. We take the 4 out in front, reduce the exponent by 1. Next one. Take the exponent out in front, reduce it by 1. So I end up with 5 x to the fourth minus 16x cubed plus 3x squared. That's the first derivative. The second derivative, well, here it is. I take the 5 out of the way, and then I take the 4 out in front and reduce the exponent by 1. It's just a bunch of repeated power rules. Next one, take the 16 out of the way, put the 3 out in front, reduce the exponent by 1. And then the last one, ignore the 3 as a constant, take the 2 out in front, and then reduce the exponent by 1, which is a 1 power, so there's no reason to write it. That is 20x cubed minus 48x squared plus 6x. There's your second derivative. Third derivative, well, there's no reason to go through full steps. I know what's going to end up happening is the 3 is going to get multiplied by the 20, so that's going to be 60x squared when I reduce that exponent. This is going to be 96x to the 1, and this is going to be 6. And if I want to do the fourth derivative, I'm going to have 120x minus 96 plus 0. So you can just keep going, and with the power rule, you can see those powers are just going to get smaller and smaller, but depending on the function, it can get more and more complicated, and we'll see later that when we get more complicated functions, taking second and third derivatives can get a little bit messy. But second derivative will have an interpretation as well with relation to the graph, but we'll get to that later in the course.